Hi, I'm going to continue with chapter 11 and just work through a few problems just to hopefully refresh some things that you did in Gen Chem 1, 107. So in order to do that, I have to hook up the camera a second. So it will always take me a minute to do this. Okay, so the problems I'm going to work from chapter 11. Get this a little bit bigger. Okay. I might have to just move the page so it's big enough. I don't want to make it smaller. Okay, so I will move the page down as we get to the last part of the problem. Okay, so this is 1145. And this just reminds you a little bit about calorimetry. So I'd better share my screen. Okay, now you should be able to see the problem I'm working on. So this problem just is a thermochemistry problem. So in chapter 11, we talked about when something dissolves, it can either be exothermic or endothermic. So this is asking us what will be the final temperature of a solution. So the question is, what's the final temperature if we dissolve this ammonium perchlorate in water? And so what we get when we do that, we don't really need to know for this problem, but to remind you, it's going to separate into ions, and we'll then call those aqueous because they're not a solid anymore. So the solution delta H is plus 33.5 kilojoules per mole, and it asks us what would be the final temperature if we make a 1 mol solution of this compound in water, and the starting temperature of the solution is 25 degrees. So if we want to make a 1 mol solution, we know that that means we want to make 1 mole of the ammonium perchlorate in 1 kilogram of water. That's a definition of molality. So I always like to put that in explicitly. So the molar mass for our compound is 117.5. And let me just see if I can switch my screen. Yeah, I should be able to go here. So hopefully you can see this screen. So I don't really like to waste a lot of time adding up molar masses. I just think that's a waste of your time after 107. So in this case, if I go to Wolfram Alpha, so just search Wolfram Alpha, and it's a software package that can do just about anything. But one thing it can do is just look up things for you. So it told me that the molar mass was 117.5. So if I go back to my Ladybug screen, okay, hopefully you can see that. So the 117.5 I got from Wolfram Alpha, and you'll be able to use that on the test. So just get used to saving time when you work problems so that you're focusing on new ideas and not just doing a bunch of tedious work. So the Q for the solution will be 33.5 kilojoules per mole. And if I'm making a 1 mol solution, I want 1 mole dissolved. So that means it's going to be 33.5 kilojoules. The mass of the total solution will be the 1 kilogram of water changed into grams, plus if I have a mole of this compound in there, it adds another 117.5 grams. So the total mass of the solution the water, the 1 kilogram, plus the 1 mole of the ammonium perchlorate, it's going to be 1,117.5 grams. So remember from calorimetry, the heat that comes out of the solution. So if this process is endothermic, that means it takes energy to make the reaction happen. And so that means that you're extracting 33.5 kilojoules from the solution. And so if I convert that to joules, that means I have that much heat when 117.5 grams of the solution, with a heat capacity, it tells you the same as water, 1.18 joules per kgram, times the temperature change. If you do that unit analysis, you will see that they both have joules and that your temperature change will either be in Celsius or Kelvin, whichever one you put your T initial in. So I solved for delta T and got negative 7.17. And so then when I solved for the final temperature, the solution went down in temperature because the reaction pulled heat out when it's an endothermic reaction. So the final temperature should be 17.8. So the next problem is one just looking at the units of concentration. So this one just, it's a problem where you have, I think this is antifreeze ethylene glycol. So it's C2H6O2. So I went to Wolfram Alpha again and looked up the molar mass. And it tells me that I start with a solution that's 40% by mass, this ethylene glycol in water. And that the density of the solution is given as 1.0514 grams per milliliter. So from that information, they want us to determine what the molarity is. So remember, you should have this on your note card. Molarity is moles per liter of solution. So if I go back to where I started with 40 grams of the ethylene glycol per 100 grams of solution. That's what 40 mass percent means. And I want to convert those units to moles of the ethylene glycol per liter of solution. So it's not a hard problem as long as you keep your units organized. So the 40 grams, if I use the molar mass, is 0.644 moles. So that's going to be my numerator. The 100 grams of solution I need to convert to a volume. So I do that with the density. So 1 milliliter would be 1.0514 grams. And if I convert that to liters, this 100 grams of solution will be 0.0951 liters of solution. So then I'm ready just to do the division. Here's my moles of ethylene glycol. Here's my volume solution that was present in. And so the concentration in molarity is 6.77 capital M, so molarity. Just one more, also fairly easy problem out of this chapter. This chapter isn't full of new ideas, just some new definitions. So 11.73 asks us to think about the solubility of a gas in a liquid. And so we're going to be using Henry's law, which says solubility, capital S, is equal to Henry's law constant K times the pressure of the gas above the solution. So the first thing that they tell us is that we have a concentration, a solubility of 1.93 times 10 to the minus 3 moles dissolved in a liter of water if oxygen's pressure is 1 atm. And so from that I can calculate K. So I can just divide this by atm. So the Henry's law constant for oxygen in water is 1.93 times 10 to the minus 3 moles per liter atmospheres. And so they want us to figure out what's the concentration of O2 in units of milligrams per liter if the pressure in our lungs is 68 milligrams or millimeters of mercury. So we want to calculate solubility. We have our K from up above. Hey, my cat's chewing on the cord. And if I convert 68 millimeters of mercury to ATM with the conversion factor that there are 760 millimeters of mercury in 1 ATM, then I get 8.9 times 10 to the minus 2. I only have 2 sig figs. And so I can calculate that at this lower pressure, the solubility of oxygen will be 1.7 times 10 to the minus 4 moles per liter. And then my little last step, because it's often given in units of milligrams per liter, I just have to convert that. So if I have 1.7 times 10 to the minus 4 moles per liter, if I convert that to grams per liter and then to milligrams per liter, I end up with 5.5 milligrams per liter of oxygen that would be in my blood at this pressure. So those are 3 problems. You'll have lots more in your homework that you can work on, but I just wanted to work through a few to make sure you are understanding and remembering how to work these kinds of problems.